The next thing I want to illustrate is the nonlinear properties that we can model in QuickField. And there's two types of superconductors, type 1, type 2 superconductor. A type 1 superconductor, such as lead, will become normal in a magnetic field greater than the thermodynamic critical field, Hc, which also decreases with increasing temperature. Type 2 superconductor, characterized by two critical fields, Hc1 and Hc2. Flux is expelled from the superconductor below Hc1, and the sample becomes normal above Hc2. So this shows a magnetization curve for both type 1 and type 2 superconductors. The type 1 superconductor, the magnetization curve is given by this dashed line here. For a type 2 superconductor, we have the solid line gives us the magnetization curve. In the type 1 case, we're plotting the magnetization minus m versus field strength. B is equal to 0 all along the curve here. And it becomes normal when we reach Hc. In the type 2 case, flux begins to penetrate the sample before we reach Hc, and then the sample becomes normal when we reach Hc2. Now the values of Hc1 and Hc2 depend on the type of superconductor. An outstanding reference, case studies in magnetic superconducting magnets, and once again the critical field is dependent on temperature, where Hc is a function of T goes as a quadratic function here. So you can see that at when T is equal to the transition temperature, Tc, the sample becomes normal and the critical field is actually 0. So in this reference, we have that for type 1 superconductors, mu naught Hc is in Tesla. So we'll have superconductor become normal in about 0.01 Tesla fields here. Now the value of mu naught Hc2 is actually quite high. For yttrium, barium, copper oxide, it's roughly 150 Tesla. So let's go ahead and model in QuickField nonlinear properties. So we have a disk of finite thickness, and I'm assigning boundary conditions for a uniform field as before, where the bottom and top edges have 0 tangential field and the left and right edges have opposite values of magnetic flux. The superconductor has a BH curve that's nonlinear. So we can use the editor here to put in the B and the H values, and above about 0.01 Tesla flux will begin to penetrate the sample here, as you can see from this entry, which corresponds to this point here on the BH curve. Okay. So let's go ahead and look at the flux distribution. And you can see it for this range of external field, we have a slight ingress of the field inside the superconductor here. So if I kind of come in here, we can see that the field is penetrating the superconductor. Around the edges, which we have a slightly greater magnetic field. Now, if I use my tool, I can see what the individual values are, local values. So here the flux density is about 0.016, 0.014 here. So that's slightly greater than 0.01, and we have some ingress of the field here.